Hey guys, welcome to this week's lecture in calculus. Okay, so this is week 9, and this week we're going to be talking about 4.1 in the textbook. We're going to start by reviewing some things that we learned about first and second derivative functions in terms of their graphs, and then we're going to use those ideas, the previous ideas that we talked about in Chapter 2 to talk about local maxes and minimums. We're going to talk about what are critical points, how do we find them, and then we're going to look at two different sort of tests to determine whether or not a local max or min exists. Okay, so let's go ahead and get started. So let's talk about some things that we looked at in Chapter 2. First derivative graphs. If the first derivative is greater than 0, this means positive. So if the first derivative is positive on an interval, then f is increasing on that interval. And if f prime is negative on an interval, then f is decreasing on that interval. So let's look at an example of a graph and its derivative and, kind of look at what they're talking about here with this first derivative business. Okay, so f is going to be the red graph right here, and f prime is going to be this blue parabola right here. And so, it says if the derivative is positive, then f is increasing, and let's confirm that's the case. Well, what does the derivative being positive means that it's above the x-axis, right? And it turns out the derivative is positive right here, okay? So what does this tell me? This tells me that from negative infinity to, what is that point? I don't know what point that is. It's close to 1, I don't know, negative 0.75, that f should be increasing. And we can see that this is the case, right? Because, as we move along x to negative infinity to x is negative 0.75, we can see that the y values are getting bigger and bigger. So f is increasing on this interval because the derivative is above the x-axis. Now look at what happens when the derivative dips below the x-axis, when it's negative. So when the derivative is negative on an interval, then f is decreasing on that interval. And we can see that that's true, right? Because starting at this peak and moving along to the right, we can see that f is getting, the y values are getting smaller and smaller and smaller. And then it starts increasing again. And that's, at this point, right? Because the derivative is above the x-axis, and so that tells us that f is going to start increasing again indefinitely. Okay, so that is a little review from Chapter 2, the graph of a derivative and a function. Now let's talk about the second derivative. So we learned that if the second derivative is positive, again, this just means positive, greater than 0, then the graph of the original function f is concave up on that interval, which means, maybe looks something like this. If, on the other hand, the second derivative is negative, if it dips below the x-axis, then the graph of the original function f is concave down on that interval. So maybe it looks something like this. Okay, so let's go ahead and look at an example. Here, the red graph, again, is just our normal f of x, and the green graph, is the second derivative. And so let's kind of analyze this. We can see that the second derivative is below the x-axis all the way till x equals 0. What does that correspond to? In the original function, it corresponds to concave down, right? And we can see that this kind of makes like an upside down U. This is concave down right here. And then once we start going above the x-axis, this corresponds to concave up on the original function. So, and we can see that this makes a right side up U shape. So this is concave up on this interval. All right, so we talked about this in chapter 2, but I just want to remind you guys, about this. Okay. All right, so we're going to use the first and second derivative to analyze this function. And the first thing we're going to ask ourselves is, where is the function increasing and decreasing? And to do that, what we're going to do is we're going to take the first derivative. Okay? If we're trying to see where the function's increasing or decreasing, we take the first derivative. So that's what we're going to do. So f prime of x, using the power rule, we're just taking the derivative of each of these guys. We get 3x squared minus 18x minus 48. All right. Now what we're going to do is we are going to we're going to set this thing equal to 0 to see where the function is neither increasing nor decreasing. Then we're going to look at, both sides of where we have a hump and use that to determine if it's increasing or decreasing. Okay, and I think it might just be helpful to just do it, and we're going to talk in detail about this in a second. But first step, we take the derivative. Second step, set the derivative equal to 0 and solve for x. So let's go ahead and do that part. So we have 0 equals 3x squared minus 18x minus 48. And let me take a quick break to get my calculator because I am lazy and it's late in the day and my brain is not working at optimal speed. So I don't want to mess this up. Okay, calculator is in hand. What I'm going to do at this point is I notice that all of these terms can be divided by 3. So I'm going to first factor out of 3 out of both, all 3 of these. So if I divide each of these by 3, I get x squared minus 6x. Now 48 divided by 3 is just going to be 16. So this becomes minus 16. All right. Now what I'm going to do is I'm in a good position to factor this trinomial. So let's do that. So factoring this, well, numbers that multiply to negative 16 that add to negative 6, I'm thinking that's x minus 8. So minus 8 and positive 2 will give us negative 6. All right, so now I can set each of these factors equal to 0. Of course, this we don't set equal to 0 because there's no x there. So we get x equals 8 and x equals negative 2. Okay, so what I'm going to do from here, so this is my step 2. I found the x values where the derivative was 0. So that means we're going to have these humps at x equals 8 and negative 2. Right, so we're either going to have something looking like that at 8, or maybe it looks like this, right, because the derivative is 0. So now we need to see what does it look like. And to do that, we look on the left and the right side of these points. So let's go ahead and do a number line. And guys, we're going to do a million examples. So, if this isn't making complete sense, I think it will eventually. So keep in mind we have humps here, but is it concave up? Is it concave down? We don't know. So let's look at this. So what we're going to do is we're going to plug in a number that's to the left of negative 2 first into the derivative to see whether or not we have a positive or negative y value. This is going to tell us whether the function is increasing or decreasing. If we get a positive number, it's increasing. If we get a negative number, it's decreasing. So we can take any number to the left of negative 2. I'm just going to be boring and pick negative 3. Okay? So what is f prime of negative 3? Is the derivative positive or negative there? Well, since my derivative is this, I can just plug in negative 3 anywhere I see an x and evaluate this sucker. Let's see. Yeah, and of course I'm just running out of space here, but this is why I have my calculator handy so I can do this kind of quickly. Let's see, what do we get? We get 3 times 9, and then we get, okay, so I get 33, which is positive. And since, this is a continuous curve, it's going to be constantly decreasing, right? Or sorry, increasing. So since the derivative is positive, since f prime is greater than 0, we know that from negative infinity to x equals negative 2, it's increasing. So let's write that. So f is increasing. Okay. Now let's see what happens between x is negative 2 and x is 8 in this interval right here. So what's happening there? Well, again, we're just going to do a little test point to see, if the derivative is positive or negative. And so I'm just going to pick a number in between these things. I'm going to pick 0. You could pick another number, it doesn't matter, but let's do the same thing. We're going to plug in this into our derivative function to see if it's increasing or decreasing. So plugging in 0 for x into our derivative, what do we get? Well, it looks like we get a negative 48. So this is negative, which tells us, remember, if the derivative is negative, it's decreasing, okay? So this tells us that I am decreasing from negative 2 to 8. Now let's look at what happens after 8. Let's pick a number after 8. How about 9? Let's see what's happening there. So again, we're just plugging in 9 into my derivative function to see if I get a negative or a positive number. Let's compute this. Okay, so let's see. Okay, so I'm getting a positive number. This is 33, positive, which tells us that f is increasing on this interval. Because we have positive, 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 okay? So what does this look like pictorially? Well, again, so the whole question is, are the humps U-shaped or upside down U-shaped? That's really what this is about on f. So at negative 2, to the left of negative 2, f is increasing. So this means, it has to kind of look like this, increasing, increasing, increasing. And then after negative 2, it starts decreasing, 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 all the way until x equals 8, okay? So it starts decreasing at x equals 8, and then it starts increasing again off into infinity. So I don't know, maybe f looks like this, but the point is that we figured out that at negative 2, we have an upside down u, and at 8, we have a regular u like this. So we have concave down right here, and we have concave up right here. So yeah, all right. So let's go ahead and, so what was it asking for? Where is the function increasing or decreasing? Okay. I'm like, what was it actually asking for? Okay, so this is our function. So based on our number line, it's increasing. It's increasing. Starting at x equals negative infinity, all the way up to x equals negative 2. And not only that, but it's increasing starting at x equals 8 on forever to infinity. And it's decreasing between negative 2 and positive 8. So that's what we were looking for. So that's our answer here. That's where it's increasing and decreasing. Okay, so that was the first derivative business, okay? Now what we're going to do is we're going to use the second derivative to see where it's concave up and concave down, even though, we kind of saw that here. Yeah, so let's see. Let's go ahead. We already took the first derivative. It was 3x squared minus 18x minus 48. What was it? 18x? Yeah. 18x minus 48. So we took the first derivative. Now let's go ahead and take the second derivative and analyze that. So taking the second derivative, again, we're just going to use the power rule for each of these guys. And we get 6x minus 18. All right, so what I'm going to do at this point is I want to see, remember, concave up and concave down, that depends on where the second derivative is negative and where it's positive, right? So the question is, when is this function negative? When is this negative? And when is it positive? And so again, we can take the second derivative and set it equal to 0, solving for x, and we get x is equal to 3. So here's our number line. Here's x equals 3. Now, if I plug in something to the left of 3 into my second derivative, how about we do 0? If we plug in 0 for x into our second derivative function. Well, we end up getting a negative number, right? This is going to be negative. And then let's go ahead and look to the right of 3 and plug in something. How about 4? So we get 6 times 4 minus 18. And this is going to give us a positive number, right? Yeah, 6. This is going to be positive. All right. So the second derivative is negative from negative infinity to 3 and positive from 3 onward to infinity. So remember, negative, that means that f is concave down from negative infinity to 3. And from 3 to positive infinity, it's concave up. Okay. So let's actually look at this function on Desmos and see if our calculations agree with that. So our function was x to the third minus 9x squared minus 48x plus 52. Right. Okay, yeah. 3x squared, x cubed minus 9x squared. Let's see. Okay. Here we go. Okay. Oops. Sorry, guys. Minus 9x squared minus 48x plus 52. Okay. Plus 52. All right, let's kind of zoom out just a little bit. Here's our function. Okay. Yeah, so it looks like it is concave down. Let's see. Concave down up until, x equals 3, which, is somewhere in this neighborhood. So concave down, we can see the upside down U shape if we sort of adjust this window. There's going to be some point of inflection at x equals 3, and then it's going to start to concave up. So let's see, where's x equals 3? Let's see. Here's x equals 3 in this neighborhood. This is where it starts to concave up, sort of in this neighborhood. And we can see that it's going to concave up indefinitely until infinity, which agrees with our math. Let's go back to the first derivative and see if that, agrees with our math. It says that the function's increasing up to -2. Let's look at our graph. So yeah, it's increasing from negative infinity all the way up to -2, which we can see right here is the sort of peak right here. And then it starts decreasing from -2 to -8. Or sorry, +8. And then it starts increasing again. And that's actually exactly what we got here. So looks good. Let's go ahead and talk about some definitions now. So the first definition is a local minimum, and we've really secretly been talking about these the whole time, but now we're going to explicitly define them. So f has a local minimum at a point P if f of P is less than or equal to the values of f for points near P. That's a little vague, but pretty much, we can have local maxes and mins at endpoints. They don't have to be on humps, but in general, if we have, so like the local minimum right here, points that are very close to it all have lower y values. That's basically what this definition is saying right here. We could have something like this though. Like this thing is also a local min. Or sorry, that's a local max. Maybe I'll draw it like this. Let's actually draw it like this. So maybe like, I don't know, maybe like this, something like this. So this is also a local min because relative to the points very close to it, it has the smallest y value. So yeah, endpoints can also be local maxes or local mins. And this is actually a local max right here because it's higher than all the points relative to it. This guy right here is a local min because it's at the bottom of a hump. And this thing right here is a local max because it's at the top of a hump. All right. So yeah, that's the whole idea. And, these are special points in calculus because that is where, at the bottom of these humps, that's where the derivative is 0. That's where the slope of the line tangent is 0. So let's go ahead and move on. A lot of definitions, but let's just get through it. How can we find a local max or min? Basically, we're going to do what we did in the first example. We're going to take the derivative and set it equal to 0. And what we get is called a critical point. So that's the, let's go back to the first example that we looked at. We took the derivative and we set it equal to 0 and we got 2 critical points. those are the points that are going to be on your number line to find the local max and the local min, or where it's increasing and decreasing. So these are the critical points right here, those x values where the derivative is 0. Okay. Yeah, so the critical value is just the y value at the critical point. And so like if this is our function f of x, we have a critical point right here because the slope of this line tangent is going to be 0. So we know for sure that, this guy is going to be a critical point, negative 0.549. And then this guy is going to be the output. That's just going to be the y value evaluating at negative 0.549. Likewise, this is a critical point. So this is going to be p. This is going to be f of p. Okay. And again, we can tell that the slope is 0 here. That's the connection with setting the derivative equal to 0. All right. Theorem 4.1, local extrema. That just means local max or local min and critical points. Suppose f is defined on an interval and has a local max or min at some point x equals a, which is not an endpoint of the interval. If f is differentiable at x equals a, then f prime of a equals 0, thus a is a critical point. So here's the important part. Not every critical point is going to be a local max or a min. We have to make sure that we draw our number line and do test values to see, is this thing actually going from decreasing to increasing or vice versa, or is it just kind of like increasing constantly? So that's when the number line comes in. And as I said, we're going to do a million examples with this. Let's get going. Okay, so here comes the first derivative test. Let's say p is a critical point. So remember, set the derivative equals 0. What do you get for x? That's p. If f prime changes from negative to positive at the critical point, then we have a local min there. If it changes from positive to negative, then we have a local max. And again, go to that first example in the video and make the connection, to these definitions here. We had our number line, right? Let's just go back to it. I just want to make sure that this point is clear. Okay, so we found these critical points, and we want to know, do we have a local max or a local min there? Well, since at this point p, negative 2, we're going from positive to negative, we have a local max here. And in the opposite case, at 8, we have a local min here because we're going from negative to positive. So this is our local min. Okay. Let's go back. And there's some pictures that you guys can copy down. This is just definitions. But, all right, let's do this one. It says use a graph of the function f of x equals 1 over x times x minus 1 to observe its local max, maxima, and minima, and then confirm your observation analytically. Okay, well, it looks like, if we plot this thing on Desmos, we get a picture that looks like this. And it looks like this guy right here is going to be a local maxima, or a local max for short. So let's confirm this observation using the first derivative test. Okay, so what I'm going to do is I'm going to first take the derivative of my function, 1 over x times x minus 1. And so here's f. And what I'm going to do so that I don't have to use the quotient rule is I'm just going to rewrite this using negative exponents. This is the same thing as x to the minus 1 times x minus 1 to the minus 1. And actually, maybe I won't even do that. Maybe I'll make it look even better. How about I distribute the bottom to give me x squared minus x, and then I can write that as x squared minus x to the negative 1. So this is f. Now let's take f prime. So f prime, I have to use the chain rule. So I have to take the derivative of the outside function times the derivative of the inside function. Well, the derivative of x squared minus x is simply 2x minus 1. Okay? Okay, so let's see. What I'm going to do is I'm going to rewrite this in a little bit, better way. I'm going to bring back the x squared minus x to the bottom. And so what this is going to become, if I rewrite this so that I have a denominator again, I have negative 1 times 2x minus 1 on top. And on the bottom, I have x squared minus x squared. Okay? And the reason I'm doing this is because, I don't really care about what happens when the derivative is undefined. I care what happens when the derivative equals 0. And that happens when the numerator equals 0. Right? If the numerator is 0, the whole thing is 0. So I'm going to set the numerator equal to 0. And what I end up getting is x is equal to 1/2 is my critical point, P. Okay, so let's confirm analytically that this indeed is a local max that we see here. So let's draw a number line. The only critical number I have is 1/2. Let's look at something to the left of it and something to the right of it. Well, to the left, what could I pick? I could pick 0. I don't think we're going to get an answer, though. Let's see. So at 0, it's undefined, right? We have an asymptote at 0 because if we plug in 0 into the first derivative, then we're going to get 0 in the denominator, so that's not good. So maybe we should pick something a little bit closer to 1/2 to the left of it. What about 1/4? Let's pick 1/4. That's smaller than 1/2, right? Okay, so if we plug in 1/4 into the first derivative, let's see what happens. Okay, so the question is this going to be positive or negative? And it's probably going to be positive because we can see that from the graph, but let's just double check. So on top, we have negative 1/2 plus 1. That's just going to be 1/2. And on the bottom, since I'm squaring something, it's going to be positive. Who really cares what it is? Positive divided by positive is positive. Okay, so this is increasing. And then let's look at what happens after 1/2. Pretty close to after 1/2. What about 1? That's after 1/2. What happens at x equals 1? Well, let's plug in 1 into our derivative. our derivative function, which is, again, right here. So we have negative 2 times 1 minus 1 over 1 squared minus 1. Okay, I think we're going to have a problem there. Yeah, we're going to have an asymptote again. Okay, so let's get even closer. Yeah, that's a problem, right? Because if we do 1 minus 1, we get 0 in the denominator. So let's get even closer to 1/2. How about, let's do 3/4. Let's do 3/4. We want to get kind of close to see what's happening here. We have all these asymptotes to worry about. All right, so I'm going to plug in 3/4 into the derivative. Get negative 2 times 3/4 minus 1, all divided by 3/4 squared minus 3/4 all squared. Okay, well, I can see that, the bottom is going to be positive. I have 9, so it's, I'm going to get a negative number on the inside, but then when I square it, it's going to be positive. On top, what do I get? Well, I'm going to get 2 times 3/4 is just going to be what? 1.5, yeah. So 3/2 minus 1 is just going to be 1/2. So we have negative 1/2 over something positive. Negative divided by positive is going to be a negative. Okay, so then we start going negative here. And so we're changing at x equals 1/2. We're changing from positive to negative, which tells me I'm going to have a hump that looks like this. So I have a local max at x equals 1/2. So that's, we verified that analytically because I'm going from positive to negative numbers pretty close to 1/2 on either side of them, depending what you mean by pretty close. But anyway, so there it is, our local max. Let's do some more examples. Here's the second derivative test. Okay, if we take the first derivative and find a critical point P, and if the second derivative at P is positive, then F has a local minimum at P. If the critical point is negative when we plug it into the second derivative function, then it has a local max. If we find a critical point and when we plug it into the second derivative test, it's 0, then the test tells us nothing. We can't conclude that it's a local max or a local min. All right, so let's go ahead and we're going to try to use the second derivative test here to confirm that, our critical points are local maxes or local mins. So first thing, we already looked at this example, but let's do it again. Let's take the first derivative. And what did we get before when we set it equal to 0? Let's see. We got 8 and negative 2. So I'm just kind of shortcutting this a little bit. So this is from the previous example. We got x equals negative 2 and x equals 8. So these are my critical points. Just set the derivative equal to 0. And we already did this by factoring. All right, so now what I'm going to do is I'm going to take the second derivative and use the second derivative test to determine if they're local maxes or local mins. Well, the second derivative, if I take the derivative of this, is just 6x minus 18. And so now I want to plug in these critical points and see whether they're positive or negative. Okay, if it's positive, it's going to be a local min. And if it's negative, then it's going to be a local max by the second derivative test. All right, so first of all, f double prime, let's test -2. The second derivative test is telling me that this is going to be 6 times -2 minus 18. This is negative. And so that tells me, therefore, -2 is a local max. All right. And we can confirm that, right? Because, yeah, so our picture, remember, when we did the first derivative test, we found that -2 was the local max. And we found that 8 is the local min by the first derivative test. Let's confirm it with the second derivative test. So second derivative test, if I plug in 8 into my second derivative function, I should get a positive number. And I do. This is a positive number. Therefore, and I'm kind of being sloppy with my language here because -2 isn't technically the local max. It's the x value of the local max. We really refer to the y value as the local max, but anyway, I'm being a little sloppy here, but maybe we should just say the x value of the local min, because it's positive. Okay. All right. Does the function have a local max or a local min? Well, I'm going to show you what the second derivative test says first and show you why we can't always use it. So first derivative is just going to be 4x to the third. And let's find our critical point. If we set the first derivative equal to 0 and solve for x, divide both sides by 0 and take the third root of both sides, and we get that x equals 0 is the critical point. Okay, let's see how we're doing on time. I know this is a long video. Okay, so this is the critical point, and now we're going to do the second derivative test. So the second derivative is, if I look at this, I take the second derivative and I get 12x squared, okay? And now what the second derivative test tells me is if I plug it in and I either get a positive or a negative number, I know where the local max and min is. Well, what happens here? A bunch of nothing happens, because if I plug in my critical point into the second derivative, I get 0, and therefore this test tells me nothing. But, the advantage of the second derivative test is that it is easier to use than the first derivative because there's no number line or any of that business. But the disadvantage is that it could tell you nothing. Like, this tells us no information. And so when that happens, we go back to the first derivative test. So what does the first derivative test tell me? Well, it tells me this. It tells me that, if I'm going from decreasing to increasing, I have a local min. And if I'm going from increasing to decreasing, I have a local max. So let's use the first derivative test here, since the second derivative test is pretty much useless here, at least. All right, let's plot my critical point on the number line, which is 0. And I'm going to look to the left of 0, and I'm going to look to the right of 0 and see what's happening. So to the left of 0, if I plug in, I don't know, -1 into the first derivative, g prime of -1, I'm just sticking it into my first derivative here, and I end up getting a negative. Okay, so negative, 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 negative. Now what happens on the right side of 0? Well, maybe I'll plug in a +1 here to see what happens on the right side. And I get a positive number. 4 is positive, so this becomes positive, positive, positive. So I'm going from negative to positive. So this actually tells me, the first derivative test tells me that at x equals 0, since, you know, my tangent is going from a negative slope to a positive slope, this thing is a local min, okay? This thing is a local min because I'm going from negative to positive. Let's confirm that this is the case with our, let's confirm that this is the case by actually plugging in the function into Desmos, the original function. The original function is x to the 4th. Let's do it. X to the 4th. And yeah, we can see this, you know, if we go down to 0, oops, let me try to zoom in here. Yeah, if we go into 0, we can see that that's obviously a local min here. Yeah. All right. So yeah, that's an instance of when the second derivative test gives us no information. But that doesn't necessarily mean that a local max or min does not exist. Okay, I'm going to stop here. I'm going to stop the video here and pick back up on this slide in the next video. Thank you guys for watching, and I'll see you next time. Hey guys, so continuing off of the last slide, we have a new definition. So a point at which the graph of a continuous function changes concavity is called an inflection point of the function. And sometimes the inflection point isn't obvious from the graph. Like, you know, for instance, right here, you know, where exactly does the thing change concavity? Could it be right here? I mean, why couldn't that be the point? And so what we're going to do is we're going to figure out what these inflection points are algebraically and confirm this with graphs. Okay. All right, so the first thing is, how do we find inflection points? Let's say that the second derivative of a function is defined on both sides of a point P. If the second derivative is 0 or undefined at this point, then that point is a possible inflection point. May not necessarily be one, but it's a possibility. And so to test whether P is an inflection point, we want to check to see whether the second derivative changes signs at P. So this is kind of a similar process to what we did with the first derivative test. Okay, so we want to find the local max, min, and inflection points for g of x equals x e to the negative x in graph G. So what we want to do is we want to keep, you know, these two bullet points in mind. So the first thing we want to do is we want to take the second derivative of the function, set it equal to 0, and then figure out what that value is. And then we're going to make a number line. Okay, so let's go ahead and when we graph this, I mean, you know, we can just kind of confirm what we gathered about the local max, mins, and inflection points by looking at the graph on Desmos. We don't really have to graph this by hand. Okay, so I'm going to kind of erase this just so we have more room anyway. So let's go ahead and first find the first derivative. Okay. And this is the starting point. Because remember, to find the local max and the local min, we can either use the first derivative test or the second derivative test, but we need to get the critical points first, and that comes from the first derivative. So first derivative, we keep the first function times the derivative of the second function, which is just going to be, using the chain rule, we just have negative 1 times e to the negative x. Keep the first times the derivative of the second, plus keep the second times the derivative of the first. Well, the derivative of x is just x. Okay, so let's go ahead and... Now what we can do at this point is we can factor out an e to the x, because all of this is stuck together with multiplication, and this is all by itself over there. So if we factor out an e to the negative x, what we're left with is just negative 1 times x, which is just negative x, plus 1, right? If we FOIL that back in, we get exactly what we started with above. Okay, so now what I'm going to do is I'm going to set each of these factors equal to 0 to find my critical points. So here I get x equals 1. Now here, e to the negative x is the same thing as 1 over e to the x equals 0. And we know that, no matter how large the denominator gets, this thing is approaching 0, but it doesn't actually equal 0. So we can kind of throw that factor out, the e to the negative x. So this guy, this x equals 1, is our critical point, or critical number. Sometimes you'll see that. And the first thing it asks us is to find the local max and the local min. And I think the easiest way to do this is with the second derivative test, if it is conclusive. If not, we need to do the first derivative test. But the second derivative test is, I think, might be easier. Well, the first thing we need to do is find the second derivative. And so let's do that. All right, so the second derivative, we have a product of functions. We have the first function is e to the negative x, and the second function is negative x plus 1. So we can use the product rule here. So we keep the first times the derivative of the second. The derivative of negative x plus 1 is just negative 1. Plus keep the second times the derivative of the first, which is just negative 1 times e to the negative x using the chain rule. Okay, so now let's go back to our second derivative test just to remind ourselves, what this says. If I plug in this critical point and I get a positive number, and I get a positive number for the second derivative, then the function has a local minimum. And if we plug in the critical point into the second derivative and it comes out negative, we have a local maximum. So let's see what happens here. And if it's 0, then yeah, we need to use the first derivative test. So let's go ahead and plug in 1. So so this is the this is the second derivative test. And just plugging in 1 for x. Okay. Well, this is all going to clear to 0 because negative 1 plus 1 is 0. So the whole product is 0. And this guy right here, negative 1 times e to the negative 1. This is negative. This is a negative number. It's just negative 1 over e. And so since this is negative by the second derivative test, or maybe we should say Okay, so since it's negative by the second derivative test, this is a local max. Okay, now what else does it want us to do? It wants us to find the inflection points. It doesn't look like there is a local min, right? Because, we only had that one critical number, and we plugged it into the second derivative, and all we got was a local max. So let's go ahead and figure out what the inflection points are. So how do we find the inflection points? Well, remember, we have to take the second derivative, set it equal to 0, and see where it's either 0 or undefined, and that could be a possible inflection point. So let's go ahead and do that. We have the second derivative right here. Okay, so for my inflection point, we're using the second derivative. And what I like to do when I'm setting things equal to 0, I want to make sure that this is like factored as much as I can. Can I factor something out? So I'm taking the second derivative, setting it equal to 0. And what I notice is that both of these things, everything's stuck together with multiplication. Both of, these terms, I have term 1, term 2, this thing, they both have an e to the negative x that I can pull out. So let's do that. So if I pull out an e to the negative x, I'm left with negative 1 for that first thing. And the second thing, I'm just left with negative x plus 1 times negative 1. And I can simplify everything on the inside to make this look a little bit better. Right? So like, if I distribute this negative 1 in there, that is going to give me, let's see. Yeah, that's going to give me a positive x, those double negatives, and then I'm going to get a negative 1. And so really, this is just 0 equals e to the negative x times positive x and a negative 2. Okay, great. Sorry about that. Let me put that in. Okay. So now what I'm going to do is I'm going to set each of these guys equal to 0 and solve for x. So remember, this thing is never going to equal 0, so we can sort of throw that out. X equals 2 is going to be my possible, here's the key word, possible inflection point. And what we want to do is we want to see if this goes from concave up to concave down or vice versa. And so we need to do our number line. This is the second part. We want to see if it changes sign. Okay, and if it does, that means it's either, going concave up to concave down or vice versa. So here's 2. And so our second derivative, where was it? Well, our second derivative is just this, right? And so if I plug in something to the left of 2, like for instance 1, into the second derivative, not 2, 1, what am I going to get? I'm going to get e to the negative 1 times 1 minus 2. And, e to the minus 1 is just 1 over e. That's positive. So this is positive. This is negative. Positive times a negative is a negative. Okay, so we're going negative, 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 negative. And let's see if it changes sign. So what happens if I plug in, let's say, 3? So something to the right of 2 into the second derivative. How about this? So I have e to the negative 3 times 3 minus 2. So this is going to be positive because e to the minus 3 is just 1 over e to the 3, which is positive. That's fine. And so, yeah, this is definitely changing signs at the point x equals 2. And remember from, way back when we talked about this, When the second derivative is negative, that's telling me my original function is concave down, right? And so what this is telling me is, yeah, this thing is concave down from negative infinity all the way up to x equals 2, and then it starts to concave up, okay? So this is the inflection point right here at 2, when it starts to change concavity. Now let's go ahead and look at the actual, and remember, what we're talking about here is the original function, the OGF. So let's go ahead and plug in f into Desmos and just confirm our findings. Or in this case, it's g, but it's x times e to the negative x. So let's see what happens. Okay, so x times, let's see, where's my e? Okay, so we're going to go e to the negative x. All right. So there we go. All right. So let's go ahead and look at what we what we found analytically. We found that the first thing we found with the second derivative test is that we have a local max at 1 on the original function. Let's take a look at this. So here's 1, and this is going to be my highest point relative to the other points. This is my local max, and then it starts to kind of, decrease off. Okay, so that looks pretty good from the picture. It doesn't look like there's any local min. So that's good. And then what else did we find? Okay, we found the inflection point. We got x equals 2. We saw that it was going, concave down to concave up at 2. So let's look at that. So does that make sense? Yeah, I mean, it's very, very slight, but that is what is happening here. It is, again, it's really subtle, and that's why, we're using, that we're doing this analytically, but it does change concavity from concave down to concave up at x equals 2. You can kind of see it sloping down a little bit. But yeah, that's the idea of that one. So let's see where we're at. All right. I'm going to go ahead and stop here, you guys, and we will pick up on this during the next video. Thanks for watching. So the graph shown is f prime of x. The question is, what are the critical points? And do these correspond to local max and mins on the original graph f of x? So remember that the critical points happen when f prime of x is equal to 0. So since this is the graph of f prime of x, we want to see where the critical points are going to be where this graph crosses the x-axis. Okay, and so, if we were to plot this on a number line, well, our first critical point, it looks like, I'm not sure, it looks like it's negative 2.75 or something like that. So let's just say it's that. And then the next one, it looks like 0. And then the other one looks like positive 2.75. So, looking at the graph, we can see that to the left of x equals negative 2.75, the function is negative. Okay, so the derivative is going from negative, and then it goes to 0, and then it starts to go positive, right? Until we get to the next critical point, which is 0. So it's positive, 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 crosses the 0 axis. After that, it's again below the x-axis, so it's negative, negative, negative. And then it's positive again because after 2.75, it's above the x-axis. So positive, positive, positive. So this is the derivative, right? So what does that tell us? So it tells us the derivative is going from negative, flattens out to 0, and then is positive. Okay, so that means that f, like this portion, maybe looks like this, right? Negative, negative, negative. So this is our function, just our regular function f. And then it flattens out at 0. And then it's positive, positive, positive slope, okay? So that's telling me that this guy is a local min, right? Because we're going from negative to positive. On the other hand, we're going from positive to negative with the next interval. Okay, so, from, maybe I'll do it like this. Maybe I'll do it like this. And then we start going, we flatten out here, we start going negative right there. So the slope is positive of f, and then it starts, it's 0 right here, which corresponds to this. And then the slope is negative after that. Okay, so that tells me that x equals 0, this guy, x equals 0, is going to be a local max because, we have this sort of upside down U shape here. Okay, and again, we're going from negative to positive at x equals 2.75. So this is going to be a local min. All right. So our local mins, we have negative 2.75 as well as 2.75. And our local max is going to be at 0. Okay, so the graph shown is the second derivative, f double prime of x. The question is, what are the inflection points? So let's talk about possible inflection points first, because remember, we need to look at the possibilities and then look to see if the second derivative changes signs. So again, just to visualize this, I'm going to put it on a number line, and I'm going to look, my possible inflection points are where the second derivative crosses the x-axis or touches the x-axis. Those are possible inflection points. Okay, so we have -3, -1, 2, and 4. Those are possibilities. And remember, if it is an actual inflection point, it's going to change signs. The second derivative is going to go from negative to positive or vice versa. Because remember, that's corresponding to the changes in concavity in f of x. Okay, so let's look to the left of -3. To the left of -3, the second derivative is negative. Negative, negative, negative. We stop at -3, and then it starts to peak above the x-axis. So it's positive all the way until it gets to -1. Positive, positive, positive. Then at -1, we're dipping below the x-axis, negative, 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 until we get to 2. But then after 2, we're still negative, negative, negative until we get to 4. And at 4, we're positive, positive, positive again because we're above the x-axis. So the only inflection points happen when the signs are changed. So this is an inflection point because we go from negative to positive. This is an inflection point because we go from positive to negative. This is not an inflection point because we're still negative. We're going from negative to negative. So that's not an inflection point. But this last one is because we're going from negative to positive. So the inflection points are at x equals -3, -1, and 4. All right, so we're going to use derivatives to find the critical points and inflection points. So our critical points come from the first derivative setting it equal to 0. So let's do it. So for this first one, we have f prime of x is going to give us 5x to the 4 minus 30x squared. Okay. Now, my critical points happen when the first derivative equals 0. So I have 0 equals 5x to the 4th minus 30x squared. From here, I can factor out a 5x squared. That's the biggest thing I can take out of both 5x to the 4 and 30x squared. And what I'm left with is just x squared minus 6. Okay. And from here, I can set each individual factor equal to 0. So 5x squared equals 0. That's going to give me x equals 0. Divide by 5 and take the square root. X squared minus 6 equals 0. If I add 6 to both sides, x squared equals 6. Now I need to take the square root of both sides, and I'm going to get a plus or minus. X is plus or minus root 6. So I have 3 critical points, and these are the 3 critical points that I have. Okay. All right, now let's do the inflection. So inflection comes from the second derivative. I do need to make a number line for inflection. So second derivative is going to be 20x to the 3 minus 60x. Then I'm going to factor out the GCF. And I'm actually going to erase some of this stuff just to have some more room. So what I'm going to do is I'm going to factor out a 20x. And remember, I'm setting that equal to 0. Okay. Now, what are my possible inflection points? Well, here, if I set this to 20x equal to 0, I get x equals 0. This part, if I set equal to 0 and solve, I get x is equal to plus or minus root 3. So I have 3 possible inflection points, but that doesn't necessarily mean that they are inflection points. We need to do the number line check. So let's go ahead and put this on number line. We got negative root 3 over here. We got 0, and then we have positive root 3. Now, since negative root 4, let's see. Yeah, negative root 4 is 2. So, let's look to the left of negative root 3, and we can actually plug in negative 2 into the second derivative. So let's do it. So f double prime of negative 2 is equal to 20 times negative 2 cubed minus 60 times negative 2. Simplify this guy out. 20 times negative 8 plus, what is that, 120? Okay. Negative 160 plus 120. So this is negative. Okay. So at negative 2, so we're going negative, negative, negative. Now I want to look at something to the right of negative root 3. How about negative root 1, which is the same thing as negative 1? Let's see. F double prime of negative 1 is, and actually, yeah, maybe I should use this version of the second derivative. That might be better to see. Yeah, okay, so, right, so, yeah, this is going to be negative 1 squared minus 3. So I'm just using the factored form to kind of see this a little bit easier. Okay, so I get negative 20 times 1 minus 3. which is negative 2, and a negative times a negative is positive. So it looks like we have found an inflection point. The first one that we found is this. This is an inflection point. Let's see if 0 is an inflection point. So let's go ahead and plug in right to the right of 0, but not bigger than or equal to root 3 is root 1, which is just 1. So let's plug in 1 and see what happens. So f double prime of 1 is just 20 times 1, 1 squared minus 3. So we get 20 times negative 2, which is negative, right? Okay, so yeah, it looks like 0 is also an inflection point. And finally, we want something greater than root 3. How about root 4, which is the same thing as the number 2? So if we plug in 2 into our second derivative, we're going to get 20 times 2 squared minus 3. And it looks like this is going to be positive, okay? So yeah, it looks like all 3 of these are inflection points. Why is that? Well, because we're changing signs at that point. We're going from negative to positive at negative root 3, positive to negative at 0, and negative to positive at root 3, okay? So, all right. So those are my inflection points. Negative root 3, 0, and root 3. And the critical points we found with the we found that earlier. Yeah, we found the critical points earlier. So, yeah, that's how we do it. Let's do another one. I'm going to erase this just because we are running out of space here. So again, we want to find the critical points and the inflection points. Let's do it. Okay. All right, so the critical points come from the first derivative, setting it equal to 0. So let's first find the first derivative. Now the derivative of 5x is just 5. Remember, the derivative of ln of x is 1 over x. So the derivative of this guy is just 3 times 1 over x, right? And I mean, you could use the product rule here, but you're going to end up getting a 0 in there, so might as well just leave it like this. I mean, you can only do this with a constant. Like if this was a variable, you would have to use the product rule. Anyway, okay, so here is the first derivative. Let's set it equal to 0 to see what our critical points are. And solve for x. I'm going to subtract 5 from both sides to get negative 3 over x equals negative 5. Let's see. What can I do here? So I know that x can't equal 0, so let's see. What can I do here? Yeah, so I can go ahead and multiply both sides by x since 0 is out of the question because of this ln of x to begin with. And I get negative 5x equals negative 3. Divide both sides by negative 5, and I get x equals 3/5. So this is my critical point. I only have one in this case. Okay. Okay. Right, so let's see. What do I want to do next? I want to find the inflection points, and to do that, I need to find the second derivative. So, okay, so my function, I'm going to rewrite g prime of x in the following way. I'm going to write it as 5 minus 3 times x to the negative 1, so I can go ahead and use the power rule. I just rewrote it like that. So using the power rule, the second derivative, I'm just going to get, this goes to 0 when I take the derivative. And then using the power rule, I get 3x to the negative 2. And then I want to set this thing, I want to set this thing equal to 0 to find possible inflection points / I want to see where it's undefined, okay, to give me possible inflection points. So this is the same thing as just 3 over x squared. And I want to set this, since the whole fraction can't be 0, right? 3 over something can't equal 0. What I'm going to do is I'm going to see where this thing is undefined. And so I just set the denominator equal to 0, right, for inflection points. And I end up getting that, the possible inflection point is x equals 0, and that's it. Now let's verify that this is actually the inflection point. I'm going to draw 0 here. Now, my second derivative is just 3 over x squared. And I think you guys can see where this is going. If I look to the left of 0, at -1 perhaps, well, if I plug in -1 into the derivative, or the second derivative rather, I just get 3 over 1, which is 3, positive, 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 positive. Then I look to the right of 0, and if I plug in, a 1, for instance, into this, I get 3 over 1 squared, which is also 3, also positive. And so it turns out that 0 is not an inflection point because we're not going from positive to negative or negative to positive. We just have positive throughout. So no inflection point for this one. We just have a critical point at x equals 3 over 5. Okay, let's do this one. So again, we're going to take the first derivative. Now, we have two functions. We have 4x and we have e to the 8x, so we need to do the product rule. Keep the first times the derivative of the second using the chain rule, plus keep the second times the derivative of the first. And now what I can do, I'm going to set this thing equal to 0, and simultaneously I'm going to factor out what both of these things stuck together with multiplication have in common. And the things they have in common is an e to the 8x and a 4. So that's what I'm going to factor out. 4e to the 8x. And then what I end up getting is, let's see. I get 8x plus 1 is what I get. Okay, so now I'm going to set each thing equal to 0. So I have 4e to the 8x equals 0. And of course, this is, e to the 8x is never going to equal 0, so we can kind of throw that solution out. Then we have 8x plus 1 equals 0, and so x is going to equal negative 1 over 8. So this is my critical point. All right. Now let's go ahead and find the inflection points, if there are any. So to do that, I need to take the second derivative, and I'm going to use this version of the first derivative to take the second derivative. Okay. So how do I take the second derivative? Well, I keep the first, which is 4e to the 8x, times the derivative of the second. Well, the derivative of e to the x plus 1 is just 8. Or sorry, 8x plus 1 is just 8. Plus, okay, keep the first times the derivative of the second. Now, keep the second times the derivative of the first. Well, the derivative of 4e to the 8x is just going to be 32e to the 8x using the chain rule. All right. Now what I'm going to do is I am going to factor out a 32e e to the 8x, right? Because 4 times 8 gives me 32. This is 32, and both of these things have an e to the 8x. So let's do that. We get 1 plus, then we have 8x plus 1. Okay. If I simplify the inside, just to make this look a little bit nicer, I get 2 plus 8x. And now what I want to do to find the possible inflection points is I want to set each of these things equal to 0. There's no denominator here, so I don't have to worry about undefined things. I'm just going to set the factors equal to 0. Now, if I set this equal to 0, 32 e to the 8x, x can't be anything to make this thing equal 0, so we'll just throw that out. Then we have 2 plus 8x equals 0. 8x equals negative 2. X is equal to negative 2 over 8, which is just negative 1/4. Okay, so this is a possible inflection point. We can't say for sure. We need to use the number line. So here is my possible inflection point. So to the left of negative 1/4, something smaller than that is negative 1/2. So let's plug in negative 1/2 into our second derivative. See what happens. Okay. All right, so let's clean this up a little bit. Now, what I have here is just 32 e to the negative 4. Now, e to the negative 4 is just 1 over e to the 4, which is positive. So, I'm going to just write this down here like this. So this is positive. Now, the second part, I have 8 times negative half is just negative 4. Negative 4 plus 2 is negative 2. So a positive times a negative better be negative. All right, so that test point, we're going to get negatives. Negative, 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 negative. Now let's see what happens at something greater than negative 1/4. How about 0? If we plug in 0 into our second derivative, we get 32 e to the 8 times 0 times 2 plus 8 times 0. All right? Well, anything to the 0 power is just 1. So what we get here is 32 times 1. And then we get 2 here. So this is positive. Okay? So positive, positive, positive. So yes, negative 1/4 is an inflection point. Okay? All right, guys, I am going to stop here. I'll see you guys in the next video. Thanks for watching. Hey guys, okay, so the directions here, we want to find all critical points and then use the first derivative test to determine the local max and min. And then we're going to check our answer on Desmos. Okay, so let's see. All right, so first derivative test, that's when we take the first derivative, set equal to 0, and then plot the stuff on the number line. All right, so that's what we're going to do. So first derivative is equal to 12x to the third minus 12x squared. Now we're going to set it equal to 0 to get the critical points. What I'm going to do is I'm going to factor out a 12x squared so that I get x minus 1. Now if I set each of these equal to 0, for the first factor I get x equals 0, and the second one I get x equals 1. So these are my critical points. And for the first derivative test, we want to plot these on the number line and look at everything to the left and the right of these points. Okay, so let's do that. So we have 0 and 1. And remember, for the first derivative test, we're using the first derivative. And I think it's easier to use the first derivative in factored form because you can see what the signs are a little bit easier. Okay, so let's first look at something to the left of 0, which happens to be -1 is to the left. If I plug in -1 into my first derivative, I get 12 times -1 squared using this factored form right here. It's -1 minus 1. So that ends up being negative. Okay. Then at 0, so a number between 0 and 1, how about a half? How about a half? So let's erase some of this, make some room. All right, so if I plug in a half into my derivative, I get this. Now, I know this is negative. This is positive. Positive times a negative is a negative. So this is negative. Oh, let's maybe do this in purple again. All right, so it doesn't, we're not changing from decreasing to increasing. So yeah, it looks like 0 is not going to be a local max or min. Now let's look at what happens after 1. How about 2? If I plug in 2 into my first derivative, get 12 times 2 squared times 2 minus 1. So this is positive. Okay. Okay. So we already know that we know that 0 is out because at 0, we're going from negative to negative, which isn't a change in sign. But at x equals 1, we're going from a negative to a positive. So that means in the original function f, it looks something like this, right? So this is f. Here's our point x equals 1. The slope, the derivative, starts negative and then it goes positive. And so this is a local min at 1. So at x equals 1, there is a local minimum. Now let's confirm that this is true with Desmos. So let's do this. 3x to the 4th minus 4 cubed plus 6. Okay. So yeah, you can see, this is f, right? And so remember, 0 was that critical point, but it's not a max or min because if we look to the left of x equals 0, we can see that, the slope is negative, and also to the right of x equals 0, the slope is negative. And so, this isn't going to be a local max or local min because of that. Now let's go to this guy. So this is x equals 1, and yeah, that's definitely a local minimum. We can tell from the graph. So yeah, let's look at this. Okay, let's do another one. All right, so we want to, again, use the first derivative test to see if there's a local max or min. Now, for the first derivative of this guy, I need to use the chain rule, okay? So I take the derivative of the outside function multiplied by the derivative of the inside function. Okay. And then what I'm going to do is I'm going to set this equal to 0. And actually, I'm going to rewrite this a little bit nicer so that I have 12x squared times x to the 3 minus 8 to the 3. And what I can do is I can set these individual factors equal to 0 to get my critical points. Okay, so right here my critical point is 0. Over here, if I take the third root of both sides, I just get x to the 3 minus 8 equals 0. Add 8 to both sides. X to the 3 equals 8. And then I can take the third root of both sides. And the third root of 8 is 2. So x is equal to 2 is another. These are my two critical points. So I need to put them on a number line and see what's going on here. Okay. So here's 0, here's 2. Yeah, and I'm going to use this version of the derivative because, you know, I can see that I have something times something, and I just want to compare, you know, if I'm multiplying a negative times a negative, a positive times a negative, whatever, because I just care about signs here. Okay, so something to the left of 0, how about negative 1? If I plug in negative 1 into my derivative, well, let's see, f prime of negative 1, and again, I'm just using what's in green here, my factored version of my derivative. Okay. Yeah, and we really just care about signs here. So this is going to be negative 1 minus 8, negative 9. That to the third, that's going to be a net negative. This guy is going to be a positive. A positive times a negative is a negative. So negative, 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 negative. Now, going to the right of 0, how about we choose 1? Maybe I should have done these test points in purple, because these aren't the critical points, these are just the test points. So f prime of 1, let's see what that gives us. This is positive. This 1 minus 8 is negative. Negative to the third is negative. So again, we have a positive times a negative is a negative. Okay, so we can already tell right off the bat that 0 is not a local max or min because we're not changing signs there. Okay, now the last thing we want to do is look to the right of 2. How about we look at x equals 3? Plug it into the derivative. Okay, so I can already see that this is positive. This is positive. Positive times a positive is going to give us a positive. So this is changing signs here. So yeah, I can see that out of the two critical points that I got, only one of them is a point of interest because it changes signs. And so, you know, this is kind of the same case, right? Because, you know, we're going from negative slope to positive slope on f, our original function. And so I am going to have a local min at x equals 2. Okay, now let's check out our graph to confirm this. So this is x to the 3 minus 8 to the 4. All raised to the 4th power. Okay, let's zoom out a little bit. And yes, indeed, we can see our local minimum in plain sight at x equals 2. There it is. All right. Very nice. All right, let's see. Okay, so now we're using the first derivative again. Same thing. I encourage you to pause the video, see if you can do this. But yeah, let's go ahead and get it done. So we have to find the derivative, we need to use a quotient rule because we have a top function x and a bottom function x squared plus 1. So remember the quotient rule. We take the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. All right. Now I can simplify the top a little bit. Let's see. So I have x squared plus 1 minus 2x squared. So this is going to give me negative x squared plus 1 all over x squared plus 1 squared. Okay, let's see. Can I do anything here? I don't think. What I'm going to do at this point is I'm going to find the critical numbers. Now, remember that the inflection point could happen when the function is undefined, but the critical numbers just happen when the derivative is 0. So the only time that this could be 0 is if the top is equal to 0, right? So my critical numbers, to find them, and again, if we were looking for inflection points, we would set the bottom equal to 0 as well, but yeah. So, all right, so we do negative x squared plus 1 equals 0, subtract 1, get that, divide by negative 1, so we get x squared equals 1, take the square root of both sides, and I get two numbers plus or minus 1 when I take the square root of 1. So let's plot it on a number line. We got negative 1 and 1. And I'm going to do my test points in purple, but these are the things that we're, these are what we really are trying to see if there's a local maximum in there. So, okay, let's do a test point to the left of negative 1. How about negative 2? So f prime of negative 2. If I plug that into my derivative function, well, I get negative 2 squared plus 1 over negative 2 squared plus 1 squared. Okay, so on top I have a negative 4 plus 1 is a negative 3 over something positive on the bottom, right? Negative divided by positive is negative. All right, so here we have negative, 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 negative. Now let's look between negative 1 and 1, perhaps 0. So f prime of 0. Well, that's going to be a problem because, wait, is it going to be a problem? No, it's not going to be a problem. Sorry, that's not going to be a problem. Let's plug in 0 into the derivative over. That is not going to be a problem at all. Okay, so what we get is 1 over 1 is 1. That's positive. All right, so it looks like we do have a local max or min. Okay, then let's look at something after 1. How about 2? So if we plug in 2 into our derivative, we get negative 2 squared plus 1 over 2 squared plus 1 squared. So the net result, well, the bottom's going to be positive. We can see that. The top is going to be negative 4 plus 1, which is negative 3. Again, negative over a positive is a negative. Okay, so this is going to negative. So it turns out that, so we're going from negative to positive. So again, we have something like this. We got a local min right here at negative 1. And then we're going from positive to negative at 1. So here, we got positive slope, then we get negative slope. So this is going to be our local max. Let's check out Desmos to see if we're on the right track. Okay, so our original function was this, x over x squared plus 1. Okay, so yeah, it looks like, we have our local min at -1, which we have here, and then we have a local max at +1. We can see that from our graph. All right. Okay, now it says use the second derivative test to determine the local max and min. Now remember, this can be inconclusive, but I think the second derivative test is easiest because you don't have to make a number line. So yeah, but if it is inconclusive, we can always go back to the first derivative test. So let's first take the first derivative, and we end up getting 12x minus 3x squared. Okay, that's our first derivative. And we want to find our critical point or points so that we can use the second derivative test. So if we set it equal to 0, we set our first derivative equal to 0, well, I can factor out a 3x. And I get that. Now if I set each of these factors equal to 0, my critical points are x equals 0 and x equals 4. So now we want to do the second derivative test with these two numbers to see if it's a local max or min. So what's the second derivative test? Well, we need to take the second derivative and plug in our critical points. So the second derivative is just 12 minus 6x. If I plug in 0, so if I plug in 0 here, I get 12 minus 0, which is positive, which tells us that we have a local min here. That's what the second derivative test says, because we got a positive number. Let's check 4. X equals 4. So f double prime of 4 is just 12 minus 6 times 4. That's going to be negative. So this is telling us that we have at x equals 4 on the original function, we have a local max. So let's check it out. Let's check out the original function, see if we're right. 9 plus 6x squared minus x to the 3. Oops. All right, so we have our local min at x equals 0, and we got that. And at x equals 4, we have a local max. All right, so we found those using the second derivative test. Let's do one more by using the second derivative test, and we'll check our answer with Desmos after. So this is going to be the last one. I know this was quite a saga, but here we go. So first thing, we need the critical points. So we have to take the first derivative. Now, I need to use the chain rule here, right? And so, take the derivative of the outside function, which is just e to the negative 2x squared, times the derivative of the inside function. Derivative of negative 2x squared is just negative 4x. Okay, now I set these things equal to 0 to find my critical numbers. Now, this is never going to equal 0, right? But if I set this equal to 0, then the only critical number I have is x equals 0. So let's go ahead and use the second derivative test. Now, I need to first find the second derivative. And, I can use the product rule here. So I keep the first times the derivative of the second plus keep the second times the derivative of the first. All right. Now what I want to do is I want to plug in 0 into my function to see if I get a positive negative number. Let's hope we don't get 0. I don't think we will. Because if I plug in 0 here, like even right here, if I just plug in 0, this whole thing goes to 0 because it's all multiplied. So let's see. If I plug in 0 here for x times -4, well, in the exponent, I just get 0. So I just get e to the 0 times -4. Now, anything to the 0 is just 1, and so I end up getting a negative answer with my critical number. So that's telling us that I have a local max on the original function at x equals 0. Let's check it out. So our original function, e to the -2x squared. All right, let's see. E to the -2x squared. Look at that. Isn't that cute? And yeah, we have a local max right there. We can see it. All right, guys, I hope you enjoyed this saga of first and second derivative test. Thank you for watching. I hope this is going to be helpful when you're doing your homework, and let me know if you guys have any questions. Thanks for watching.